Good day everyone. So I am again Michael C. Pasis from Mapua University. So welcome to our online electrical engineering review and tutorial channel. So today we will discuss the series RLC series circuit or series RLC circuit under the topic of series parallel RLC, RL and RC. So today we need to verify one important formula in terms of how the circuit behaves in an RLC series circuit in terms of voltage. Okay, let's have the circuit first. As you can see, when you say an RLC series circuit, you have an R and L and C are connected in series. They have the voltages VR, VL, and VC respectively being injected by a voltage V or total V. But here, we're considering an AC circuit. Now, we need to review what we have discussed from the past lessons, that the current will always be constant and the voltages around the loop in a series circuit will always be the summation of all of the individual voltage of the components. So from here, we just imply the Kirchhoff's voltage law. Okay, now before we go to the phasor diagram development, so we need to have the voltage and current conditions when you're considering the phasor diagram. So when I say phasor diagram is the implementation of the voltage and current angles. However, before you do that, you need to know the conditions in every component. First, if you have a capacitor alone injected in a circuit, the voltage will lag the current by an angle of 90 degree. Or it means, in other words, if we interchange the reference, remember the right of the statement is reference. So in this case, if we interchange that, it will become I leads the voltage by a certain angle 90. So this is the same. They are the same. Okay, you just place the voltage at the reference side of this statement. Now, in an inductor type, if that is alone in a circuit, the voltage will lead the current I by 90. So this is the opposite on a capacitor. Always remember that. Or in other words, if we interchange the reference, it will become I lags the voltage by 90 degree if that is alone in the circuit. So please take note of that. So simply we will make use of this on some problems which needs the analysis of vectors. And in terms of resistance, well, whatever the signal is, if an AC or an DC signal, okay, the voltage and the current will always be in phase with each other. So it simply means whatever the injected voltage, if you have a resistor alone, V is in phase with I or I is in phase with B. Okay, let's have the phasor diagram now. As we can see here, we need to know the first the reference. The reference is the current. It's very obvious because the current is constant. And we need to make first we need to place the vector diagrams of V and I in terms of a resistor. As we have mentioned, okay, the voltage and current are what? In phase with each other. So voltage and the current are in phase with the resistor. So this for the resistor part. Okay, next we go to the inductor. So in the inductor, the voltage will lead the current. So if your current is a reference here, it's very obvious that if you turn the angle in a 90 degree counterclockwise direction, okay, so we have already mentioned this one on some of the lessons, that is 90 degree leading. So when you say 90 degree leading, the voltage and the current will lead, the voltage will lead the current by 90 degree. So the placement of the V here is simply your inductor. And last but not the least, the voltage will lag the current now by a 90 degree fashion here. Okay, if you turn the angle in a clockwise direction, okay, or 90 degree, this is positive degree for leading, VC will be located here. We need to get the vector sum, this for the capacitor rather. We need to get the resultant of VL and VC, and we can have this, no? Considering VL has, consider only, no? VL is greater than VC in terms of magnitude. Okay? So, VL minus VC will be the resultant of the voltages of your reactive components. And thus, considering again, no, a phasor, no, you can now get the total voltage VT here by having the vector sum of VL and VR respectively. Rather, your total Vx, which is VL minus VC and VR respectively. And considering only magnitudes, we can develop this equation here that total voltage VT squared is equal to VR squared plus VL minus VC squared. Now, as you can see here, we're considering magnitude. Whatever the much higher magnitude, for example, the higher magnitude is VC instead of VL, you can use VC minus VL respectively, but again, it will become positive simply because it will square the value. So, considering only VL is greater than VC, well, the equation is VL minus VC squared, or if VC is higher than VL, you can consider VC minus VL squared. But anyway, either way, the answer is absolute or positive. So we can make use of this as well, no, on some of the problems. Or you can use also, there's no squared here or square root. Okay. So, other way around, they are the same. Next, we will discuss parallel RLC circuits. Hello once again. So, from our last slide, we discussed the series RLC circuit and the corresponding equation which is involved, which is in terms of voltage. Now we will discuss the relationships of RL and C, and we must develop an important equation as well in terms of the total current. And here you can see the behavior and relationships of the components. Okay, let us recall the parallel circuit during your DC circuits. This is the same way. One characteristic is the voltage is constant all throughout, and the current will be the total current will be dependent, okay, on the summation of all of the currents of the individual components. So by applying KCL, IT here simply IR plus IL plus IC respectively. And the voltage is constant because the voltage in parallel on the branches will be the same all throughout without any interfering components. Okay, now let us also recall what we have discussed from the last slide in terms of voltage and current relationship. So this is the voltage and current relationship. What I did is, since our constant component is voltage, we make use of the voltage as our reference here. So what will be the relationship in terms of the current and voltage if our voltage will be our constant parameter? So for a capacitor, I will leads V by 90 degree. For an inductor, I lags V by a 90 degree. And whatever happens, as I have mentioned from the last slide again, that there in a resistor, the current and the voltage will always be in phase. So in this case, I will be in phase with V, or simply in other words, okay, the vectors of voltage and current, okay, will be in phase with each other. Okay, so I think I will make use of black pen so that you can see voltage, current. Okay, let us go to the phasor diagram. In the phasor diagram, as you can see here, our main reference is the voltage, so we make use of the current and the voltage for a resistor are in phase with each other. Also, in terms of the capacitor current versus the voltage, okay, you will have here a 90-degree, okay, 90-degree angle. Positive because that is leading. And here, you have a negative angle, 90-degree, or a lagging condition for your L. Because as you can see here, with respect to the reference, you need to, okay, rotate the angle in a clockwise direction for a lagging condition. I forgot to mention this one from the previous slide, but I take this opportunity now, that this angle theta here, as you can see, okay, considering again that IC, or assume that the current C, or the capacitor current, is greater than IL. But whatever happens, as I mentioned, is since we're considering magnitude alone, this magnitude alone, whatever happens, the value of the total current will be positive. Okay, for this angle theta here, if we consider this circuit, IT and the voltage V, as you can see here, this angle theta is the value of the power factor angle. Wherein when we say power factor, okay, that is the cosine theta of the input circuit. And the theta here, which is the angle between the source voltage and the source current, the angle. Or in other words, you can now get that theta here, which is dependent on the angle of voltage and the angle of current, which is simply equal to theta Vs minus theta Is. So another important equation that you need to know, which is very, very important as well in determining power factor angles, which we can describe on the next lesson, the power factor angle, or power factor relationship between R, X, and Z, or even on powers, which is S, P, and Q. So just subscribe so that you can be informed on the following lessons. Okay, now we have the opportunity to solve some problems.